Hello students, welcome to EPG Pathshala. I am Dr. Shaukat Mir from Hamdard University, Delhi. Today we are going to talk about a module named Evaluation of Fixed Oils, Fats and Waxes under the paper Pharmaceutical and Biological Analysis. After completing this module, the student will be able to understand following. Number one, definition and types of oils and fats along with waxes. These constitute these lipids. They will also understand a little bit about the chemistry of lipids, various parameters for the evaluation of fixed oils, fats and waxes also will be discussed. And last of all, analysis of individual oils, fats and waxes along with the associated ingredients that are often found along with this. So let's first understand what are these oils, fats and waxes. Actually, fixed oils, fats and waxes, they are the part of a major phytochemical class called lipids. They are present in plants and they are present also as well as in animals. So they, along with sterols, they make this phytochemical class called lipids. They encompass substances that can be extracted by organic solvents like petroleum ether or solvent ether, hexane, etc. All these organic solvents, they are able to extract or separate these constituents from the plant matrix or the animal matrix. They are of wide distribution. They are found in plants and animals alike. In plants, these constitute the coating layer over leaves and fruits and other parts of the plants. Besides, they are also mainly found in seeds and fruits. In animals, these fats and waxes and these fatty acids, they are obtained from the skin, appendages, liver and other adipose tissues. The conventional method that is employed for the extraction of lipids includes solvent extraction. As we understand that these solvent extraction can be percolation, it can be maceration, and maceration along with which can be carried out in Soxhlet apparatus or in percolators or macerators. Another method is expression, where you press these samples containing these fixed oils, fats and waxes under very high pressure so that you get these constituent isolated from the matrix. Or the last method is heating, which is in a way melting these semi-solid or these solid substances. These are also, as I told already, that these are soluble in light petrol, hexane and hot alcohol. They are insoluble in water. So these properties are utilized for their extraction when we want to separate them from plant matrix or animal matrix. Pharmaceutical, these are of very importance. They are useful. They are used as cream bases, as ointment bases, or in some of those cosmetics. They are also used as coating agents and vehicles for intramuscular or these intramuscular injections. Besides, they are also used as nutrients, which are like nutraceuticals, as well as in the preparation of emulsions and lotions. The examination of the mixtures such as ointments containing fats, oils and waxes is mostly based on the estimation of their known constituents, and it provides a reasonably accurate assessment of their method of preparation, whether they have been prepared as per the prescribed methods or not. This slide gives the chemical structures of fats, oils, and wax constituents, as well as some of those sterols. They together make this class called lipids. So on the left hand side, you can see these are fatty acids. So at the top, it is an unsaturated fatty acid. In the middle, there is an saturated fatty acid, and at the base, there is a C40 unsaturated fatty acid. Towards the right hand side, top we find these fatty acid glycerides, which are the part of fixed oils, or phosphoglycerides like lecithin. So here we find that glycerol makes important part of these constituents, and they are esterified with either with 1 or 2 or 3 units of fatty acids, or sometimes they may also be esterified with a phosphate group or a substituted phosphate group, which are known as phosphoglycerides. Again, towards the lower panel, you find some of those fatty acid esters, which are the parts of waxes. So these are the esters of long chain fatty acids with long chain alcohols. So they are present in like carnauba wax or supermacety. So associated products like sterols, they are found along with those fats and oils in plants and in animals. So the examples are these constituents which have been shown towards the lower right hand panel, cholesterol and stigmasterol. Visual presentation of various parameters for the evaluation of oils, fats and waxes. So you find these physical parameters like specific gravity, solubility, melting and boiling point ranges, refractive index and optical rotation, along with viscosity, fat content and rancidity. So these parameters, they are the chemical parameters, they are the physical parameters that are used for the evaluation of oils and fats and waxes, while as the values like iodine value, acid value, acetyl value, ester value, peroxide and hydroxyl values, along with the saponification value, they represent the chemical parameters. They are based on the chemical composition of these oils, fats and waxes. The first important method for the estimation of quality of for the estimation or the analysis of fatty acids or fats and waxes is the acid value. It signifies or it shows the condition of these fixed oils, fats and waxes, because the increase in acid value is related to the rancidity of these substances. Acid value refers to the number of milligrams of potassium hydroxide or sodium hydroxide that are required to neutralize the free acids in 1 gram of the substance. So this condition, this is the general condition, whereas there can be some individual, there can be variation as per the individual monographs. It is the measure of the condition of the oils, as rancidity of the substances is accompanied by the formation of free acids, which are estimated by this value. This method is satisfactory as long as the volume of alkali that you use is not very large. Where if the volume of potassium hydroxide or sodium hydroxide, which are of the strength of 0.1 normal, if it is required, is more volume is required, or the volume required is less than 2 ml, more dilute titrant may be used. If the oil has been saturated with carbon dioxide for its preservation, generally we reflux the oil or the substance with alcohol ether mixture for 10 minutes before titration for the removal of this carbon dioxide. It can also be accomplished by exposing the substance in a shallow dish in a vacuum desiccator for 24 hours before weighing the test sample for analysis. There are two methods for the estimation of acid value. Number one method involves take about 10 grams of substance and dissolve in 50 ml mixture of alcohol and ether. So this mixture is already neutralized to phenolphthalein. So this sample solution is mixed with 1 ml of phenolphthalein, and it is titrated with 0.1 normal potassium hydroxide or 0.1 normal of sodium hydroxide. till the solution turns faint pink, and that color remains till at least 30 seconds. The acid value is then calculated by using the formula mR multiplied by V multiplied N whole divided by W. mR is the molecular weight. For potassium hydroxide it is 56, and for sodium, if we use sodium hydroxide, it is 40. V is the volume of potassium or sodium hydroxide used. N is the normality of these solutions, and W is the weight of the sample taken in grams. The other method is where we use a solvent mixture of isopropyl alcohol and toluene. So it is also neutralized before titration to phenolphthalein. So it is titrated. This phenolphthalein is added till a pink color persists. Then a well-defined or accurately weighed quantity of the sample is added to this solution. The quantity to be taken is mentioned in table on the right hand panel. So that solution is shaken and then it is titrated with 0.1 normal potassium hydroxide or sodium hydroxide to an endpoint where the pink color persists. So the calculation of acid value is same as that of the method stated earlier, method 1. Next important parameter for analysis is iodine value. It represents the number of grams of iodine absorbed by 100 grams of sample under prescribed condition. It is the measure unsaturation of the sample. Various methods and modifications have been devised. So iodine value greatly varies based on the method followed. So it's very important that the method should be stated very clearly, and the condition should be adhered very strictly as mentioned in the methods. So one such method is Bridges method, where is added to a 10 ml solvent, and to this mixture add 20 ml iodine monochloride solution. So it is kept in dark for an appropriate time at 15 to 25 degrees Celsius. Then we add an excess of potassium iodide and water, and this excess is then back titrated with 0.1 normal thiosulfate. The iodine value is then calculated on the basis as a product of volume of 0.1 normal iodine absorbed multiplied by equivalent factor into 100 whole divided by the weight of the substance taken for analysis in grams. The another method is Hans method. So here the quantity to be taken is mentioned in table 2. So the sample, as per the iodine value expected, that much weight is taken and it is dissolved in 10 ml of chloroform, and we add 25 ml of iodobromide, attach a stopper in the vessel and allow it to stand for 30 minutes under dark with occasional shaking. Now add 30 ml of potassium iodide and titrate the liberated iodine with 0.1 normal sodium thiosulfate. The solution is thoroughly shaken after each addition. When the iodine color becomes quite pale, add 3 ml of starch and continue titration with 0.1 normal sodium thiosulfate till the blue color is discharged. Blank test is also performed at the same time. Then the calculation of the iodine value as per the formula given. So where AR is the atomic weight for iodine, VB and VS are the volume of the sodium thiosulfate with the blank and with the actual sample, and N is the normality of sodium thiosulfate. Hydroxyl value is defined as the number of milligrams of potassium hydroxide equivalent to the hydroxyl content of 1 gram of sample. The procedure is that we transfer accurately weighed quantity into a glass stoppered conical flask. So the quantity to be weighed and used is determined as per the table given on the right hand panel. We add 5 ml of pyridine acetic acid reagent, and then it is securely plugged and followed by heating on a steam bath under reflux for 1 hour. After that, add 10 ml of water and heat it on a steam bath for 10 minutes, cool it, and add 25 ml of ethyl alcohol, previously neutralized to phenolphthalein. First, 15 ml is added by pouring through each condenser. After removing condenser, washing the sides of both the flasks with the remaining 10 ml portions. So blank is also performed. To each flask, add 1 ml of phenolphthalein and titrate with 0.5 normal alcoholic potassium hydroxide. Record the volume in ml consumed by residual acids in test solution as T and they consumed by the blank as B. Then the hydroxyl value is calculated as per the formula given below. While as if the acid value for the test substance is known, then you can use the calculation of hydroxyl value as per the formula given in the lower panel. Pyridine acetic acid anhydride reagent is prepared freshly and is used once it is prepared, and it is used once you have completed the process of preparation of this reagent. The peroxide value is the number that expresses milliequivalents of active oxygen, the quantity of peroxide contained in 1000 grams of substance. This test must be performed promptly after sampling to avoid oxidation of tests. The procedure goes like this. Place 5 grams of substance in a conical flask. So add 30 ml of a mixture of glacial acetic acid chloroform 3:2 ratio. Shake it to dissolve. Add 0.5 ml of saturated potassium iodide solution. Shake for exactly 1 minute and add 30 ml of water. After following procedure as shown, add 5 ml of starch and continue titration with shaking till the blue color is discharged. The peroxide value can be calculated as per the formula given on the screen. So Vt and Vb represent the volume of sodium thiosulfate consumed in actual test and in black test, while as N and W represent the normality of the thiosulfate and W is the weight of the substance taken. Another significant analysis is through the determination of saponification values. So this parameter is based on the hydrolysis reaction of lipids, and here it is expressed as the number of milligrams of KOH that are used to neutralize, that are required to neutralize the free acids that are present in a substance, as well as to neutralize those which are generated by hydrolysis of these substances. So a weight of 1 gram is usually required for is used for this analysis. If it is for some of them, they are separately mentioned separately if more volume is to be needed. This is a measurement of glycerides present in oil and is determined as given now. So the procedure goes like this. To about 2 grams of substance, we add 25 ml of 0.5 normal ethanolic potassium hydroxide, and then we reflux it on a water bath for about 30 minutes. So then we add phenolphthalein as indicator while it is still hot, and we titrate it with an excess of alkali, which we titrate the excess of alkali with 0.5 normal acid. So mind you that this acid can be both either sulfuric acid or it can be hydrochloric acid. We also repeat the experiments by omitting the oil, so that will give us the blank titration. The saponification value is then calculated as as a multiple of as a ratio of the ml of 0.5 normal alkali absorbed multiplied by equivalent factor of 0.2805 multiplied by 100 and overall divided by the weight of the substance taken. So the control experiment needs to be taken immediately, and the titration of the excess alkali after saponification should be made as soon as possible. The titration of the alkali with standard hydrochloric acid is preferable to HCl is preferable to sulfuric acid, as the hydrochloric acid gives a more soluble potassium salts. Adding a small excess of 0.5 normal acid and by back titrating it with 0.1 normal alkali gives more accurate results or more accurate endpoint. Another important value for the analysis of these substances is Acetyl value. It is defined as the number of milligrams of potassium hydroxide that are required to saponify the esters in 1 gram of substance. It is as is evident that it will be it is the difference between the saponification value, which is the total value, minus the acid value. So this difference between the saponification value and acid value represents the ester value. The procedure goes like this: we place 1.5 to 2 grams of accurately weighed substance in a 250 ml flask. Then we add 20 to 30 ml of the neutralized alcohol and shake the sample carefully. Now add 1 ml of phenolphthalein and titrate with 0.5 normal alcoholic potassium hydroxide and till the free acid is neutralized. Now add 25 ml of 0.5 normal alcoholic potassium hydroxide and heat the flask on a water bath or a steam bath under suitable condenser to maintain the reflux condition for 30 minutes. So after refluxing, you add titrate the excess potassium hydroxide with 0.5 normal hydrochloric acid. Perform blank titration under the same conditions. Then the ester value is calculated as a product of molecular weight of the potassium hydroxide and a product of the difference of the volume used in blank and the test conditions multiplied by the normality and whole divided by the weight of the substance taken for the test in grams. After discussing saponification value, we understand that there is considerable amount of substances of oils, fats and waxes that remains unsaponifiable. This is the basis for unsaponifiable matter. So it represents this portion of the substance that are not saponified by alkali hydroxide but they are soluble in ordinary organic solvents. For estimation of unsaponifiable matter, the procedure is as follows. We transfer 5 grams of accurately weighed oils or fats in a conical flask. We add alcoholic potassium hydroxide, then followed by heating on a steam bath under suitable condenser to maintain reflux for 1 hour with frequent shaking. The reaction mixture is cooled to temperature 25 degrees Celsius. The contents are transferred to a flask fitted with polytetrafluoroethylene stopcock. This flask is rinsed and the washings are added. Then extract with 100 ml of ether 3 times and add 40 ml of water. Gently shake the separator for a few minutes. Avoid violent agitation as it may result in formation of difficult to separate emulsion. Allow the mixture to separate and discard the lower aqueous phase. Wash the ether layer with 2 additional portions of water. Wash the extract successively with 40 ml portions of potassium hydroxide till last washing is not rendered is not rendered by addition of 2 drops of phenolphthalein. Transfer the ether extract to the tarred flask, evaporate the ether layer and add 6 ml of acetone to the residue. Remove the acetone in a current of air or the dry residue, dry it till the successive weighings do not differ by not more than 1 milligram. The unsaponifiable matter is calculated using the formula 100 into VRS by Vs. VRS is the weight of the residue and Vs is the weight of the oil or the fat taken. Another important parameter for estimation of oil is acetyl value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the acetic acid freed by hydrolysis of 1 gram of acetylated fat. The oil is acetylated with acetic anhydride, which combines with hydroxyl group present in the fatty acids. Since most of the fatty acids, they don't contain a hydroxyl group, excepting some of those racinoleic acid as shown in the lower panel. So in castor oil, the acetyl value is high, about 146 to 150, owing to large amounts of hydroxy fatty acids known as racinoleic acid. So it is a modification of oleic acid, so which differs because from that of oleic acid, as you can see, there is an additional OH group in racinoleic acid which is not present in oleic acid. Let's now discuss some of those miscellaneous methods for the analysis of fatty acids and waxes. The first test is solubility test. We understand that oils, waxes, fats are soluble in organic solvents like chloroform, alcohol, etc. They are insoluble in water. These solubility patterns, they are used for the preliminary analysis of these substances. Another method is translucent spot test. Fats, waxes and fixed oils, they don't evaporate at room temperature due to higher boiling point ranges. When these substances are placed on a sheet of paper, they diffract light. The diffracted light can pass from one side of the paper to another side and it produces a translucent spot. So the production or the appearance of translucent spot on paper is the basis of this test, and it is given by fats and fixed oils. So it is in contrast to the test, it is not provided by the volatile oils. The another test is acrolein test. It is particularly for animal fats like butter. So here the sample is treated with a dehydrating agent like potassium bisulfate. The glycerol portion of the molecule gets dehydrated to form an unsaturated aldehyde named acrolein. So it has a pungent irritating odor. So the appearance of acrolein confirms the presence of these fats. The other methods for the preliminary determination for the preliminary analysis of fatty acids include fat content determination. So where the powdered sample is extracted with solvent ether in a Soxhlet apparatus for about 4 to 6 hours. The extract is filtered in a pre-weighed flask. The solvent is evaporated and the residue is dried at 100 to 105 degrees Celsius till it attains a constant weight. A parameter that is applicable to animal fats particularly is volatile acidity. So where these small fatty acids like butyric acid, which are volatile in nature, they are steam distilled, they are collected by Clevenger apparatus, they are collected in a definite weight of the sample and their content is determined, and this gives volatile acidity content of these animal fats. Some of these physical parameters for analysis of fats and waxes are refractive index. As we understand that this is the ratio of velocity of light in vacuum to the velocity of light in substance. So it is a very important parameter for its analysis. So refractometers are used, and the oils like cassia oil, arachis oil, castor oil, their refractive index can be used for their analysis and quality check. Their values are provided. Optical rotation is another important feature for the analysis of fatty acids. Here we have provided a list of showing the optical rotation of some of those important fixed oils like castor oil, which ranges from plus 3.5 to plus 3.0 degrees. Chenopodium oil minus, it is a levorotatory oil, minus 30 degree to minus 8 degree. In the same way we have clove oil, which has optical rotation from 0 degree to plus 6 degrees. So the oils, because of their constituents which are dextrorotatory or levorotatory or a mixture, so they have their optical rotation which is recorded, and it serves as a parameter for their analysis. Melting point of these particularly fats and waxes which are either in semi-solid or solid state, so this also acts as a method of determination of the quality of these products. So as we understand, so melting point apparatus is used. So with the higher molecular weight and more saturation of these fatty acids, the samples they range from semi-solids to solids. So accordingly their melting point ranges, and in case of liquids their boiling point ranges, they are used for the analysis of some of those constituents and substances. Specific gravity is another parameter which is used for the estimation of many of those liquids. So pycnometers are used, or specific gravity bottles are used. So the method goes like this. We take a clean, dry, calibrated pycnometer or this calibrated this specific gravity bottle. We fill it with recently boiled and cooled water at 25 degrees Celsius. We adjust the temperature of the sample to about 20 degrees and fill the sample in a pycnometer, maintaining the same temperature of 25 degrees Celsius. The ratio of the weight of this test sample to that of the reference sample gives the specific gravity of the sample. The other method is by the determination of densities of the samples. Oscillating transducer density meter is used. So several of those handheld samples in these models are available. Basic diagrams is shown on the right hand panel. So the difference, that the ratio of the density of the sample liquid to the density of the water, which is usually taken as 1 gram per ml at 25 degrees Celsius. The other method is by the determination of densities of the samples. An oscillating transducer density meter is used. So several of those handheld samples in these models are available. The basic diagrams is shown on the right hand panel. So the difference, that the ratio of the density of the sample liquid to the density of the water, which is usually taken as 1 gram per ml at 25 degrees Celsius. Viscosity is another feature. It is a physical feature which is used for the analysis of fatty acids, fixed oils and fats. So it is recorded by either rotary viscometer or capillary tube viscometers. The detailed procedure is given on this slide. Now let us go to the specific standards for oils, fats and waxes based on our previous discussion. So this table shows some of those fats, oils and waxes which are either pharmaceutically important or they are industrially important. Their saponification values, iodine values, acid values and their composition, main composition is given. So you can see like almond, it has a saponification value of 183 to 200, very high saponification value. So it has a high iodine value also because of its oleic acid and linoleic acid content. Now coming to this castor oil, you find that its saponification is higher. At the same time, because of its racinoleic acid content, it will have a higher acetyl value, and acid value is not more than 2. So other samples for which the standards have been given in this table include olive oil, lard, spermaceti. Some of those waxes also have been mentioned. So like these wax has a saponification value of which is actually an ester value of 70 to 80, and iodine value ranges from 8 to 11. Consists of mericyl palmitate and cerotic acid free acids. So because of which its value is acid value is very high, 18 to 20. For wool fat, which is obtained from wool, so its values, they are also given. So it consists of mainly these sterile esters. So students, let us now summarize what we have learned in this module. We have understood that these fixed oils, fats and waxes, they make a very important phytochemical class called lipids. So they, along with sterols, they are jointly known as lipids because they are the substances that are extracted by organic solvents like light petrol or petroleum ether. So they are liquids, or they are semi-solids or solids. These are extracted by solvent extraction. And we have also learned that they can also be extracted by expression using hydraulic pressures, or they can also be extracted by melting, which is heating, and so that this solid material melts. So this may be followed by some associated steps like filtering, freezing, steaming, for example in case of castor oil, and washing and decolorizing for making it more refined. A number of quantitative tests are commonly used to evaluate the oils, fats and waxes. So for example, these acid values, saponification values, ester values, iodine values, they are based on the chemical nature of these substances. We also have some of those physical constants for oils and fats that are used for the analysis of these substances. For example, specific gravity, melting point determination, refractive index and viscosity determinations are very significant as far as their analysis is concerned. These tests, both these physical tests as well as these chemical quantitative parameters, they provide a detailed insight of the quality as well as the composition of these substances, which are these fatty acids, fats, oils and waxes. Thank you.